Are we still recording? Okay. Do I need to restart? Okay. Okay, so back to our lecture. So I'm very happy that we spent 2 hours to cover the design procedure, redesign procedure, and how do you mathematically find new design variables. So let's say I give you examples, give you an example of how it truly look like if we apply optimization. But just based still not based on the real not based on the real data. Okay, so if you go back to see, we actually had one formulation. We said we want to minimize negative speed of x. Okay, so let's just talk about speed. Let's forget about the constraints. So if we are minimizing negative speed of, we could have more variables, x1, x2, da da da, okay? And if we truly want to solve this by Newton's method, what's gonna happen? So this will be a multi-dimensional minimization problem, right? We have a lot of variables. So in this case, again, initial gas. So it's like you need to make gases. So it's okay to have a new design with some gas. And usually you're not lucky. Your first design may be poorly performed. However, if you have a strategy, a nice design strategy, maybe the next design could be better. So initial design, initial gas, right? What's next? Then you find you have some issues because this is only one multi-dimensional, right? You need to solve for the gradient. You need to do this. What is this? What is the gradient vector for multi-dimensional? Let me show you. Partial f, partial x1, plug in your gas. Partial f, partial x2, plug in your x. da, 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 then you may have a lot of variables, right? Let me use my eraser and draw a bigger bracket. So, if this is the case, how do you know the function of S and all the X? How do you know? You don't. If you have a soft robotic design, how can you understand the mathematical equation about the speed and all the dimension? No, you don't know. So, for example, another practical example, if I have this a design, right? The one I show you, the pneumatically controlled soft robot, okay? And we could have many variables. Let me just give you examples. This could be x1, this could be x2, and we have air bubbles inside, right? We have air bubbles. We can have, for example, the thickness of the wall, x3, and maybe we could have the height of the legs, x4. We could have maybe the width of the legs, x5. We can have more. We can have so many variables. For every variable, what do we truly want? We want to know the speed, function speed of x1 to xn. What does it look like? Every time you change the design, the speed changes. But if there is no function, you don't know the function, how do you do derivative? So the problem is, how do you do derivatives? The derivatives when f is unknown. That's the issue. Even you have really good math, you know how to do Newton's method. Here's an issue. You don't know the function of speed. So now I'm going to teach you one method called finite difference. Method of finite difference. Okay, that helps you to estimate the derivatives. Okay, so how do you do this? What you are looking for is partial f, partial xi. You don't know this, right? So what you can do is you can have, sorry, I need to go back. Well, maybe like this. Okay? How do you do this? So what you can do is to estimate in this way. F of x of k, now very importantly, plus a small value of delta. But this is a vector. This is a vector. Delta is a scalar, a number. So you only plus delta at specific part of the vector. So here I'm going to multiply something called EI, okay? I will tell you what is EI later on. Minus f of xk over delta. So what is EI? EI is the ith normal vector, unit normal vector, unit normal vector. What is it? Again, what is it? It's actually either 1 or 0 when I shouldn't do that. I should say it's like a vector 0, 0, da, 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 and one of it is 1, the other is 0. And this particular one is the ith component. So in the past, what you usually know is actually I, J, and K. What are I, J, and K? In here, you can say it's E1, E2, and E3. What are they? They are actually 1, 0, 0, 0, 1, 0, and 0, 0, 1. So why do I do this? If it's a three-dimensional problem, then how do you estimate this? How? You can do this based on what I told you. It's an estimation. F of using the current value plus some delta times E1 minus x of k over delta. What is that? What does that mean? Okay, let me talk in human language. It's like this, F, and let's say you have x1k, x2k, x3k, and then plus delta. It's like this, plugging in this value, minus f of x1k, x2k, x3k. Okay, over delta. Again, talk in human language, please. So another example, let's say I have a function f equals to sine of x. Okay, I want to know what is f prime of, for example, x equals to maybe 1/3 of pi. 1/3 of pi. I want to know what is it. So in this case, I'm not going to directly derive it. I'm not going to differentiate. I'm going to use so-called the finite difference. So in this case, the finite difference would be, I should give you a two-dimensional problem. Sorry. Let me use a two-dimensional problem because the example was two-dimensional. So what I can do is cosine x. How about this? So it's two x1 and x. So make it written nicer. X1, x2. Very simple problem. Now, I want to know what would be the not first order, it's a second order, so it's like a partial f, partial x1, but over where x1 equals to 1/3 of pi, x2 equals to, for example, 1/4 of pi. Tell me how do you get this? So when you do that, what you actually do is actually f of the current value, pi over 3, pi over 4, and you want to plus some small value, for example, 0.1, minus pi over 3, pi over 4, over 0.1. This will gives you the estimation of partial f, partial x1. if you just plug in. Okay, so how to plug in? Do I need to plug in for you? So it's like sine pi over 3 plus 0.1 plus cosine pi over 4 minus sine pi over 3 minus cosine pi over 4. I don't need a bracket, sorry. Yeah, it's like this over 0.1. If you do this, then that will gives you the estimation of the partial derivative with respect to x1 at particular point. Okay, so the idea is like this. Take a look at the current situation. You never need to know the function, actually. So imagine this whole thing. Imagine this whole thing. I just copy this and then paste here. Imagine this whole thing is a black box. We sometimes would like to call this black box. Imagine this is something you don't know. So I can call this a black box. So over here, basically, you'll just plug in some number into the black box. So whenever in real situation, when you plug in numbers in the black box, it's just like changing the variable a little bit and then testing its performance. So this is just like changing variable a little bit and checking the performance. Right? Because F is your performance. You change a little bit. This is what you change, just by a little. Okay? So if you can do that, if you can evaluate partial derivative, then you actually can compute everything over here. Oops. Computer not so happy. Oops. What do I do? Replugging. No, I think the problem is iPad. Replugging iPad. iPad is not happy. Now we're back. Okay. So that means we can actually solve for everything inside the gradient vector in any black box problem. Black box problem means you don't really know the relationship of the function f. Oops. iPad really not happy. Okay. Change, replug in. Okay, now we're back. So let me try to continue. Now, so as I mentioned, in a real problem like this, if you want to maximize the speed with respect to so many variables inside your soft robot, you don't know exactly the speed. What's the function of speed in terms of, oh my God, it's getting crazy. In terms of the, maybe I can use iPad to log in Zoom because I don't really need this guy. I can use my iPad. But you can continue to record. I just log in as a different account. Yeah. So now my iPad is not cooperating. I will stop sharing. And then I try to log in by iPad. In this case, your recording is over there, right? Over on your side. But is in your computer or my computer? In my computer. So if I unplug this, it doesn't matter. It's just for display. Right? The Zoom is still there. Okay, so we can do this. Okay, so the classroom should be able to see it, but I need to zoom this screen. I think my OBS crashed. That's why. No, it doesn't show. Hold on. Try again. Maybe click streamer. Let me try OBS again. I think maybe the OBS was crashed. So but I need to share. I need to share screen on Zoom. Share. Okay, and then I do this. And then turn off this guy. No. Okay, so my iPad is not cooperating. Maybe I stop using iPad. Okay. Am I still sharing? No, right? I will turn off OBS because it's crashing. Okay. So just Google Meet, right? So for the last part of my introduction, I will just use a Word file. Okay. Can you see the Word file? Yes. Okay. Okay. So as I mentioned earlier, you may not be able to get the function form of the performance with respect to the variables. So the function actually is a black box. What does the black box mean? You plug in variable values and it returns function values back to you. So it's just like you can make designs with specific variables and you test its performance. The performance, I should say the resultant performance is just like a black box. Okay, so later on when you make designs, whenever you create a design as a black box, you still don't know the exact function relationship between that performance and all of your variables. But when you make one design, it's like a one try. You define your parameter, you test it. Okay, so besides optimization, is there a good way to help my design process? Okay. So there's something I would like to share with you that creates the function form. So you can use regression model to create function form of the performance. Why is it good if you have a function form? If you have function form of the performance, you can easily take derivatives. Then you can use optimization methods such as Newton's method to find the optimal solution, optimal design variables. Okay, so now I want to teach you how to do regression models. So what happened when you want to have regression models? So usually this is the case. Usually you will have, for example, M designs. And in each design, you have different combination of variables. Okay, so for example, this is a design number 1. Then you can have, for example, x1. This time I'm going to use trying to find a way to define the symbols so you won't be confused. Let me use a comma 1 and x1/2, x1/3. Okay, I think just 3 variables. Okay, just 3 variables. So in this particular case, so what does where xi, j is the the jth variable in ith experiment. Okay? Is it easy to understand? Right? So x11 means the first variable in design number 1 or experiment number 1. So you could have more designs, for example, up to design number m, because I said there are m designs. So in this case, you will have variables like the mth design. This is m. Okay. So it's like you try, for example, 10 different designs, and there are 3 parameters, 3 variables in each design. So after you have the design, what do? You test its performance. So over here, what you would do is you test its performance. And let's say the performance is called y or f. And so basically the performance is a value of, I can say f of 1, okay? So f of 1 means fi is the performance of the ith design. I can say that xi is the ith design, right? So f1 is the performance of the first design. So similarly, over here, you will test the performance of the mth design. So over here, this is m, right? So what do you have so far? You have a lot of x, and you have performance f. You want to build a model based on those trials. And it's a regression model. So how do you build it? You can now do this. You can, let me think about it. Put it vertically. So this is f. I should use I can use a Google Sheet. That's easier for the matrix expression. Okay, just a Google, just eat faster expression. Just create a Google Sheet. Okay, so you want to now place all those information you know in matrix form. So here you place F1, F2, F3, and of course, dot, dot, dot. The last one, Fn, okay? I'm going to use this underline, okay? You do it like this. And this is a vector. This vector will equals to another, oh, sorry. We want to say that equal. Equals to what? Equals to a matrix. And the matrix will be given in a certain way, and that matrix basically will be defined based on the model you use. So I'm going to define a model form. So I'm gonna say the model form could be f equals to a, how about say a, capital A times x1 squared plus b times x2 squared plus c times x3 squared. Okay, then d times x1 plus e times x2 plus f times x3, and then plus a constant g. Okay, so 1, 2, 3, 4, 5, 6, 7. 7 constants. A, B, C, D, E, F, G. However, we don't know the value of those yet. Because if I know the value A from A to G, that means I know the function. But actually, I don't. Because think about this. F is the speed of your soft robot. X1 and X2, X3, they are just 3 dimensions in your soft robot. How can I know the function? So right now, the regression method can help you to estimate the relationship between speed and the 3 variables. And this is how you can do it. Over here, just like how the model wants you to do, you want the first one to be x1 squared, second one x2 squared, then x3 squared, x1, just like how the model says, x2, x3, and then the constant. Constant, just put 1. Okay? So later on, I need all these being placed in a matrix form, but following this order. So I'm copying this to everywhere, but not just pure copy. For this particular one, x1 squared, this is going to be x11. Oh, sorry. This is going to be x11. Yeah, this is going to be, here I should say 2. This will be x12. This is x13. Okay, similarly, this is x11. This is x12. This is x13. Okay, in the next column, this is going to be x21, x22, x23, x21, x22, x23. Okay, again, x31, x32, x33, x31, x32, and x33. Okay, finally, this is xm1, xm2, xm3. Almost done. Once I finish this, we will finish today's lecture. Almost done. So now I will have a bunch of numbers. Everything this is like I'm putting them in a matrix. This is a vector. I'm using a box to represent this is a vector. Okay, and this will be placed in a matrix. Okay, let's check the dimension. This is actually a m by 1 vector. What is this? This is, sorry, m by 7, right? We have n rows and 7 columns, right? So you put them in this order. Later on, you want this matrix to multiply something. Multiply something. Multiplying the constant that you just you need for the coefficient. So over here, this is going to be A, B, C, D, E, F, G. You put them vertically right here. And this one, Let me use a color. Let's use this color. This is going to be placed in a vector as well. So what's the dimension for this? This is 7 by 1. Okay, take a look at the way we put everything together. And we can check one by one. F1 equals to x11 squared times x plus x12 squared times b plus x13 squared times c plus x11 times d plus x12 times e plus x13 times f, and then plus a constant times g. So what is this? This is exactly plugging in the first experiment into this model, right? So that forms one equation. And I have m designs. That's why I have m equations. So at the end, I have this beautiful matrix form. All the values in blue is known because you try m designs, you choose your own x1, x2, and x3, m different combinations, and you test m times, so you have m different performance. Everything you don't know is the coefficient from A to G. So what you want to do is to calculate A to G. So let me take a picture of this whole thing. Okay, take a picture. This. So this is what you are doing. You put everything into this vector and matrix form. So I'm going to call the yellow vector as a capital F. It's a vector. I'm going to call this huge blue matrix capital, let me call it capital, which one I didn't use. Let me just say capital X, how about this? And then times the coefficients right here, I'm going to call it the, call them Y, how about this? Okay, so Y is unknown. Can someone tell me how do you solve for Y? Anyone from the Zoom? If I have, you can see my screen, right? Yes. Okay. So anyone from the audience? If I have F equals to X times Y, and I'm looking for solving for Y, what do you do? Can I move X to the left? How do I move the X to the left? Anyone? Anyone cares? My story about America didn't inspire you? Okay, nobody cares? Anyone breathing? Am I still here? Who am I talking to? Anyone? How do I move X to the left? Inverse, good. So can we do this? X inverse times F equals to Y. Can we do this? Let's do a voting. If you think we can do this, you can type in +1. If you don't think you can do this, type in -1. If you don't type anything, that means you are not here. You are a robot. Who thinks +1 means you think we can do this? -1 means you think we cannot do this. This is your today's homework. If you don't give me comments, you miss your homework. Okay, now I'm gonna do the same thing on the classroom. Raise your hand if you think you can do this. Okay, 2 votes, 3 votes, 4 votes, 5 votes. So one person say no, one person say no. Okay. Oh yes, I got response from students. I'm so happy. Thank you for responding. I'm happy. I'm going to give you homework score. Okay, so most of you think we can do this. Okay, I'm still waiting for more response because that's your homework. Today's homework. The classroom, the 6 people in the classroom already raised their hands. I'm still waiting for whoever is online to say +1 or -1. If you are still here. Yes, okay. So now we have 2 -1. Most of you say +1. 3 -1. Yes, thank you. Is there anyone looking for voting? Okay, more -1. Okay. Good, very good. You just got your homework score. Thank you. Anyone wants a homework score? Okay, I'm stopping here. So if you still want to comment on this, you can. If you don't, you lose your homework score. Okay, that's your homework. Comment, give me a comment, I give you a score. Okay, now I'm releasing the answer. No matter if you say +1 or -1, you get the homework score. Okay, you got a full score of your homework. So everyone in the classroom got the homework score. Now, I'm going to tell you the right answer. The answer is we cannot. Why? Why can't we do this? Because X is not a square matrix. It cannot be inversed. So what do? There is a way to do this. This method is called least square approximation, and it requires some optimization with error minimization, and you don't want to know what's going on. It's too much mathematics. Just understand it's based on optimization. So the result of least square, I'm almost done. Bear with me. Least square approximation is the best fit with minimal error. So it's a fitting model. Not exactly correct, but it's the best fit. Okay? That's why it's regression. The final result is you will multiply transpose. Do you know transpose? On both sides of the matrix. So you multiply X transpose on both sides. Over here. Okay? Where T is transpose. Okay? After you do that, you check your dimension again. Check this one. Check the dimension of this guy. So what is X? The dimension of X is n times m by 7. So the dimension would be 7 by m times m by 7. So at the end, you will have a matrix of 7 by 7. It becomes a square matrix. So if you have a square matrix, what can you do? Inverse. You can inverse. So you can inverse this guy, this whole thing. So at the end, the final equation is over here. you have this, right? But you will, this whole thing, the underlying entire thing will be inversed. So this whole thing will be inversed. Take it to the front. This whole thing will be inversed. And then multiply this. Also multiply. So at the end, this is the equation. Okay, it doesn't look nice. It doesn't look nice, but that's how it's done. So all the coefficient in y can be done by, let me show you how. X transpose. So the transpose of this multiply itself, the whole thing take inverse, multiply the transpose of this, and then multiply f. Okay? If you don't believe it, let's try it here. Okay? Let's put some numbers here. I will just put 1, 2, 3, 4, 5, 6. And let's say, let me create a new function. So for example, let me create a function. What is the function? I want to copy this whole thing here, right? And copy these here. And I want to show you how it's done. Give me a minute. Okay, so over here, I need to create some data. Over here, let's say I have 1, 0, 1, 1, 2, 1, 5, just random combination, right? -1, 3, 4. Okay, 1, 2, 3, 3, 0, 4. Okay, let's say you try 5 different experiments, and the f, I'm going to use the same function. For example, this is going to be sine of x1 minus cosine of this, and times x3 squared, just some random function. Okay, so if you truly do that, if the true function of f and these three are these, that what you will get at the end, it will be a matrix like this. Okay, so I'm gonna plug in those numbers. So it's like you made 5 experiments, you test the performance, you got 5 values. You're going to plug in those numbers over here. I'm gonna paste the value only here. Okay, so those are the 5 performance you got. So over here, you will have the square root of this guy. So you can copy this whole thing. Okay, you have the square root of these, and you have the square root of this guy. I can copy the whole thing. Square root of this guy, right? I'm just copying. And over here, this will be this guy. So I'm just copying. Okay. Copy. So if you do it right, it's gonna be like this. Okay, so it's like plugging in those numbers. So if you truly want to, oh, there's a 1, there's a missing 1 here. If you truly want to inverse this, it's impossible. But you can transpose this. So the transpose of the m by 7 can be done. I'm doing this here, transpose. I'm transposing the whole thing, right? I'm transposing. So what you will get at the end is like a vertical matrix. This is after transpose, okay? This is after transpose, okay? So I'm going, what does this tell me? I need to do transpose, and then I want to transpose times itself. So I'm going to do the basically the X transpose transpose times X. So basically matrix multiply. And here, this is the transpose one and times the original one. So what you get at the end is a 7 by 7. Is it 7 by 7? Yes. So this is the 7 by 7 matrix. Okay. So now what do you do next? Let's check. Okay, I now have this guy, right? I need to do inverse. So I need to do inverse of this guy. Inverse of this guy. Okay, I just inverse it. So inverse means INV. No. NINV. Yes, of this guy. Okay. No, it doesn't help me. Not invertible. No, not invertible. I was not lucky. I create a matrix that is not invertible. That means I need to change this. Okay, sorry. I create some problem that is not invertible. Let me correct some values. So it could be invertible. Okay. How to, maybe I change the position of those. 1, 3. Is it better? No. About 0, 0, 0. 0, 1, 0. No, not helping me. 2. Why? Should be able to be reversed. Maybe I should try more experiments. Okay, because maybe that's a problem. Give me a second. Almost done. So maybe I just need more. So I'll just copy the whole thing here. Copy the whole thing here. And then when I transpose, I need to transpose up to I10. Right? Oh, then I'm out of space right here. I will just cut, paste it here. Okay, so it's 10 by 7, so this becomes 7 by 10. So over here, I will change it to K18 here times itself C2 to I10. Okay, now it's inversible. Is it? I21, C21 to I21, C21, I27. Yes. So this is the inverse of it. Now, what do? I need to multiply X transpose T. So this guy multiply X transpose T. This is the transpose. So find matrix multiply this guy. This is the inverse multiplying the transpose here. Okay. So I get a bunch of values here. What do I do next? Multiplying the F. So at the end, this whole thing, matrix multiply. There's a bunch of numbers multiplying my F. F is here. F is here. Okay. So what I should get at the end would be 7 values. 1, 2, 3, 4, 5, 6, 7. So what does that mean? That means the model is this value times x1 squared plus this value times x2 squared plus this value times x3 squared plus this value times x1, this value times x2, and this value times x3 plus a constant, this value. So the summation of all these, that's the model. So if you have this polynomial model, you can do derivatives so easily. Take derivatives. And then you can use Newton's method or any other method to solve for it. Okay, so I'm sorry today my iPad didn't function pretty well with me, but I covered what I want to introduce for today. And tomorrow I will spend some time on more time about design of experiments. And I hope tomorrow my iPad will be functioning better. Okay, so I will send you this spreadsheet. It's just an example. So I hope you can use it to understand inside the math what happened. Okay, inside those math what happened. Let me change the color. Maybe this. Okay, so this will be the end final result. So this is this guy. That was at the this part. That was this part times x transpose. And finally, if you times the whole thing right here. Okay, so just but as I mentioned, this was very random example, very random and random experiments, very random. Okay, so I hope you have a little sense about doing experiments. You can have multiple trials. You can change your variables. You can test the performance. But if you want to understand the behavior between the performance and the variables, you can build a model. It doesn't need to be this long. When you build a model, how do you get a coefficient? This is one method. The least square approximation is the method. Okay? And the approach was done and shown in the spreadsheet. Tomorrow we can talk more about design. Only 1 more hour, then I'm done for the lecture. Okay, that's it for today, and thanks for responding to complete your homework. Thank you. That's it. Bye bye. Peter， 那检查一下谁有回应，然后就是 homework， 就 homework 就是他们要确定6个都有，他们都有回应，好，都写下来。对，那就没有回应就是没写功课。OK， 好，那就这样子咯。那我就关掉，对不对？我先 leave meeting， 好，我先 leave meeting。那我 assign 给你。